Well, I'm very pleased that we have Gabriella Pinter. She leads wonderful sessions and has actually been out and visited us in some schools in person and works as a mentor. I think Anna Wold can talk about what it was like and has been like to talk with Gabriella in our mentoring program. And I'll pass the torch over to Gabriella.
Hi. Good morning, and thanks for your nice introduction. I'm Gabriella Pinter. I am a math professor at the University of Wisconsin-Milwaukee. I've been here for 22 years, and I really like math circles and working with students and teachers on fun math problems. And I hope that you are going to enjoy the one that I selected for today. And maybe we can start. I would like to share my screen. I can do that, right? Yes, okay. So you can see my screen now. Is that correct? Thank you.
Yes, we can see your screen.
Okay, let me just do a little bit. I'm trying to have two screens so I see people while I'm sharing. It's a little bit nicer that way. So this activity is called Square Game. It's not my activity. I found it in a book, but I really enjoyed it, and hopefully it will be interesting. So it starts the following way. It's a game two people play, and the first player chooses a rectangle. The rectangle has integer dimensions. So let's say in this case, I'm the first player and I chose these dimensions. It's 9 by 24. So after that, so this is player 1 choosing the dimensions of the rectangle. Then player 2. And what player 2 does, player 2 needs to draw in the largest square possible in such a way that it is flush with the shortest or the shorter side of the rectangle. So if you are player 2, you draw in a square which has dimensions 9 by 9, right? So I'm doing this, okay, right? So you draw this square. And now it's player 1's turn again. And player 1 also draws in the largest square possible in such a way that it has to share a side of a previous square, and it has to leave a rectangle if there's something to be left. Okay, so what's the largest square that we can draw in? Please just say something, or if it's not clear, please ask.
Nine by 9.
9 by 9, right? So this side is 9. We still have a rectangle left that is going to accommodate a 9 by 9 square. So again, we draw in, player 1 draws in a 9 by 9 square. So this was player 2, this is player 1. It's player 2's turn again to draw in the largest square possible in such a way that it shares the side with a previous square and it leaves a rectangle if there's something to be left.
6 by 6.
6 by 6, right? here we have 6 left, so it's going to be a 6 by 6 square right here. So this is player 2. Okay. So what will player 1 do? This was 6, so it's 3 left. The largest square we can draw in is 3 by 3. And it can go either here, so either one of them is fine, right? So let's say player 1 does this one. And then player 2, it's a square left. So player 2 draws in that last square. And in this case, player 2 wins, because player 2 drew in the last square. And there's nothing left. Can you hear me all right? I had a message that somehow the line was not good. Okay, I'm good. So this is the game, right? So would somebody give me dimensions? Let's play another one. So it is a little bit clearer what we do. So now you have a chance to be player 1. Choose dimensions for a rectangle. Natrina, please. Oh, you are. Anybody, just please unmute yourself. Tell me some dimensions.
Someone put in the chat 27 by 12.
Oh, good. Great. 27 by 12. Okay.
Hi, before you start, I have a question. Does the dimensions have to be an even number, or can you use an odd number and an even number?
You can use any integer. So it doesn't have to be both even or both odd. One can be even, one odd, or both even, both odd. All is possible.
Thank you.
Maybe I should look at the chat. Sorry, I can bring that up too. Okay, so if we have 27 by 12, so this is 12, this is 27. So player 1 chose 27 by 12. Let's see. So player 2 draws in the first square. What are the dimensions of that square? 12 by 12, right? So we have 12 here. So player 2 did this square. Now it's player 1's turn again. Can player 1 fit another 12 by 12 square?
If this is on Jamboard, I'm going to guess not.
Yes, in a little bit. I just wanted to do maybe one more example.
Oh, sure. Okay, wonderful.
So I do have a Jamboard to share. Right now I am on OneNote, if that was the question. Okay, so player 1 can still draw in a 12 by 12 square, right? So this is 12. And maybe my drawing is not very nice here, because what is left after that was 27 length. So what's left is just 3 here. So what's the next move for player 2?
3 by 3.
3 by 3, right? Okay. Player 1 also does a 3 by 3. Right? This is 3, this is 3. We have 12 originally, so we have 6 left on this side. So there's another possibility for player 2 for a 3x3, and then player 1 finishes it with the last 3x3. Okay, so in this case, player 1 wins. So this is game 1. And in game 1, you can see the way we went was always drawing in the largest square possible, and the players alternate. And you cannot be tricky, right? So when a rectangle is left, you cannot draw the square somehow in the middle. You always have to leave a single rectangle when you draw in a square. So this is game 1. Should we, maybe let's play one more game. So would you like to give different dimensions here? These were somehow suspicious, right? In the end, we got a 3x3 square. Here, we also got a 3x3 square in the end. The last one to make a square wins, yes, in this game, yes. So maybe let's try a smaller example, larger. Okay, 35x28, nice, okay. So if we do 35x28. So 28, 35. So this is player 1's choice, right? So player 2 draws in the first square. What's the size?
$30 by 40. No, 30 by 15.
Wait, so one dimension is 28, right? So the largest square that will fit will have side 28, because it cannot be more. The 35 by 35 does not fit a rectangle. So it would be a 28 by 28. As many of you are saying in the chat, player 2. Right? Okay, so if this is 28 here, then we have 7 units left in the length, and we still have 28 in the height. So it's a 7 by 28 rectangle left. So player
7 by 20. 7 by 20.
Sorry?
7 by 7.
7 by 7, right? And maybe it does not look that nice, but you can sort of see. So it is a 7 by 7 for player 1. Now, what's left here? We got 7 off, 28, so 21 by 7. So player 2 can also do a 7 by 7 here. I know it does not look like a square because my drawing is a little bit off. But it's another 7, so now we have 14 left. So player 1 can do a 7 by 7, and player 2 finishes with a 7 by 7. So here player 2 wins. And the last square was a 7 by 7. So if you think about these 3 games, kind of the starting dimensions and what we got in the end, is there anything that kind of any kind of pattern that jumps out at you. We had 9 and 24. We ended up with a 3 by 3 square. We had 27 and 12. We also ended up with a 3 by 3 square. We had 28 and 35. We again ended up with a 7 by 7 square. So there is something about these numbers here. Many of you are saying in the chat that it's somehow connected to multiples and divisors. And indeed, 3 divides both 9 and 24. 3 divides 27 and 12. The 7 divides both 28 and 35. And not only they divide both of those numbers, but they are the largest common factors of those two numbers. So that's an interesting thing, that this game, when it ends, seems to give us this greatest common factor, someone said in the chat. But is that always the case? Yes, so it definitely seems to give the greatest common factor, but let's try to test that a little bit more. So would you like to choose some more dimensions to test this idea? So let's try maybe another one. Oh, 51 by 17. Nice. Okay. So 17 by 51. Maybe I'll try to draw a little nicer. Okay, so if this is 17, that's too long, right? So what's going to happen here? So player 2 goes first. What's the largest square? 17 by 17, right? So this is the 17 by 17 square that player 2 will draw in. It's player 1's turn. How much is left here on the length? $34, right? So again, player 1 can make up a 17 by 17 square. Oh, yeah, player 1. What's left is exactly a 17 by 17 square. And with that, player 2 finishes the game. So with 17 by 51, if we go back to our list, we got a 17 by 17 square in the end. And that confirms our idea that, yes, what we are left with is very much connected to the numbers that we started with, and it seems to be the greatest common factor of those two numbers. So any more ideas what we should test? And maybe something smaller. So let's just test this one. Let's say we do a 9 by 5. And I will try to write this or draw this nicely. maybe it's a little too small, but okay. So 9 by 5. What will player 2 do? Five by 5, right? So now 4 is left here. And the other dimension is 5. So this was player 2's square. Player 1's square is going to be a 4 by 4 because there's only 4 left here. So 4 by 4 is the largest one that player 1 can draw in. And now there's only 1 left in the length, in the height. So we have a 1 by 4 rectangle. The largest square that fits that is a 1 by 1, exactly, right? So this is player 2. And now it goes just like that. Player 1, player 2, player 1. So with 9 and 5, we ended up with 1 by 1 squares. And also player 1 won, if that's any interesting. So there could be many questions connected to this, but let me show you a variant of this game too. So sometimes it seemed that we were drawing many of the same size squares. Right? In the very first game, player 2 drew a 9 by 9, and then player 1 also drew a 9 by 9. Right? In this game, in the 35 by 28, we had them drawing 7 by 7, right? Several times. So the idea in game 2 is that if you can draw in a certain size square, you draw in all of that size squares that you can. And I have a picture that maybe shows this a little nicer. So I made a slideshow of this too. So this was game 1, right? Where player 1 draws in the square, player 2 then goes largest square possible, then player 1, then player 2, and then again 1 and 2. So the change in game 2 is that once we have this rectangle with integer sides, player 2 goes and, okay, this is, the colors are messed up here, I'm sorry. So player 2 is blue, or actually, the numbers are messed up, right? So this should be 2 here. So player 2, I cannot draw on this. Sorry. So, but the idea is this, that whoever goes doesn't just draw in 1 square, but will draw in as many of that same size square as fit in that rectangle. So the player who goes first here, oops, doesn't just draw in 1 square, but since they can fit 2 of that same size, they draw in both of them. And then the same thing happens with the other player, and the game is a little bit shorter in that way. I'm sorry, maybe I can do this in here to show you, for example, with the 17 by 51, if we are playing game 2 variant, then what would happen? Player 2 can draw in a 17 by 17, but not just 1, they can draw in another one, and they can draw in another one, and the game is over. So in one step, the game is over and player 2 won. You see, player 2 won in the original game too, in game 1. But the game took, let's say, 3 steps or 3 moves. Here, it was just 1 step or 1 move. And we can revisit the previous games, the 27 by 12, how many steps game 1 takes. Maybe I'm different. Right? Player 2 went 2, 3, 4, 5, 6 steps. While game 2 would be shorter, right? Player 2 would draw this square and also this one, because that's the same size. And then remember, all of these were 3 by 3 squares. So player 1 would draw all of them. So game 2 would only take 2 steps. Okay, for our first one, 9 by 24, game 1 was 1, 2, 3, 4, 5 steps. 5 squares were drawn in, right? Game 2, how would that go? Player 2 would draw this square and this square too. Then player 1 draws a 6 by 6, but can only draw 1 6 by 6 square because no more fits. But after that, we have a 3 by 6 rectangle, and player 2 can draw both of these squares in. So in this case, it's just 3 steps. And then maybe with this last one, game 1 was 1, 2, 3, 4, 5 steps. 5 squares were drawn in. Game 2 would be player 2 draws this one, and these are all 7 by 7. They look really not squares, but if we are looking at their dimensions, they should be squares. So player 1 draws all of them in, which means 2 steps. So maybe at this point, I stop, and I did make a Jamboard. I can put the link for the Jamboard in. So I think what we could do, maybe open up some breakout rooms. Maybe now that everyone's back, would you like to share what you did in the breakout room? What kinds of observations you made? I see several people saying the group did great. So what did you find interesting? What did you find out?
I would like to share. I'm Trina Bigdam from Page Unified School District. So in our group, we were trying to find a pattern of how many outcomes to get a square from the rectangle. Because my thinking was that if we were to have like a 5 by 5, I thought, no, a 4 by 4, I thought that we can have 2 outcomes of 2 by 2 squares. But David made it clear that we had to get the biggest square out of that square first, the 4 by 4. So that one was only 1 outcome. And then we tried to find a pattern, but we didn't get done. But yeah, it was fun.
Great. Yes, so you always draw in the largest square possible.
Our group works with a wide variety of students, and we discovered that it doesn't really matter the age group. You can start at a very young age. to introduce them to the greatest common factors, and it works all the way up to high school. So that's what our group really liked about it, is that it can work for almost any grade level.
Mhm. Yes, I think you can certainly introduce this activity at a very young age too. You don't even need to mention greatest common factor. It is not easy for younger kids to get this idea of largest to draw in a largest square. I did this activity once with elementary school kids. Sorry, it's very echoey here. I don't know. And the students took quite a long time to get that idea of largest square drawn in. So if you do it with young kids, they take the time to so that they get that idea and kind of go from there. Any other interesting things you'd like to share?
I also wanted to include, I agree with the previous person because I teach K to second and I'm a SPED teacher, so a resource teacher, but this type of thing will keep them busy. And not only that, like they can identify like their numbers and identify like what a square is, because a square can be any size. It can't just be a 1 by 1. It can be like any size. So it gets them that idea of, you know, squares have equal sides, and if it's unequal, it's a rectangle. So in a way, I guess teaching younger kids in elementary, they can get the idea of just number identification and just knowing what truly a square is, and learning the math terminology of equal sides. So it doesn't have to just go back to multiplication. Like this will actually keep kids busy, because it kept definitely our group busy. We're trying to like fill in all the squares possible, but yeah. But yeah, I just want to say thank you for sharing. That's a really good way to teach math and squares and stuff. But thank you.
Good morning. This is Ella Gilmore from Kayenta. I teach first grade, and I was thinking about a simple way of applying that with shapes and numbers, because they're, I noticed the group I have, you know, with the COVID and just being on virtual and not being online every day, I noticed that I had to go back and review a lot of intro to shapes and numbers. And I'm thinking I probably really have to simplify for them to use the same idea. It's just not at a higher level. But I was just thinking of that, and I was trying to share, but just trying to join the groups took a while. So that's all I have to share. Thank you.
Thank you.
I was listening in on this group. So first they discussed the rules. They also had a bit of discussion understanding what the numbers that were prepared down the column and the numbers down the diagonal meant. It took a little bit, but after they figured out what that was, you know, we put the time sign up there to say that we're making, you know, blank times blank rectangles. They started drawing the rectangles. And they started making guesses and figuring out patterns and explaining why, which was really wonderful. So they quickly figured out that on the longest, biggest diagonal that it was all ones, because if you have a square, you can only put in one square if you're making it as big as possible, and that filled it up. Yeah, so The next pattern that they noticed is that if they go down the first column, 1, 2, 3, 4, 5, because if you just have a single row or column that's one thing wide, then they filled in 4 more numbers, but they didn't yet see what the pattern was, which is understandable. It's kind of a complicated pattern. It takes a while to figure out the pattern, but I think they were making very good progress.
Absolutely. So this is an interesting thing. And once the students get into the groove of drawing these rectangles and then counting up the number of steps the game takes, again, once the dimensions are given, it's determined. So you can always play it out. There's no real decision for the players. You can start to see wonderful patterns in this, both for game 1 and game 2. And it also brings in the question of, all right, so who wins, right? Sometimes the kids like that, sometimes not so much. But in all these games where you put a 1, right, in that main diagonal, those are not good dimensions to name at the beginning, right? Because whoever names those dimensions, like 4 by 4, will lose, because the other person just draws in the whole square and the game ends, right? Now, if it's a 4 by 2, you said it takes 2 steps. That's good for the person who named 4 by 2, right? Because that person will win. So player 1 wins the 4 by 2 game. And sorry, my computer is acting up a little bit. It cannot get into this. So which games are won by the player who named that dimension, and which games are won by the other player? That brings in an interesting aspect of this too, right? So if I try this game is won by who said 4 by 2. Agreed? Is that okay? Because if this is 2, this is 4. Player 2 is going to draw in a 2 by 2, and then player 1 can draw in a 2 by 2 and finish the game. The 4 by 3 game is also won by the person who named those dimensions. Right? We can play that out. Let's see. So if this is 4, this is 3. We have the 3 by 3, and then there's 1 left here. And this side is 3. So this was player 2. The 1 by 1 will be a player 1. Then it's player 2 again, and another 1 by 1 by player 1. Okay, so these stair steps, what they are trying to mean is that you work with these numbers, right? Let's say 3 and 5. Those are the dimensions of the rectangle that we are examining. So that's how this table was made up, that you look in the column and you look in the row, and then you figure out how long the game, where the dimensions were 3 by 5, how long it will take. And it was calculated that it's 4 steps. And if it's 4 steps, you see 1, 2, 3, 4, in 4 steps, player one wins. So which games are won by player one? This one, exactly those. Do you see any pattern on these numbers here?
It's all the even numbers. So the even turns is what player one would win.
Mhm.
Or yeah, player one.
Yes, exactly. Right? Whenever it takes an even number of steps, player one wins. The one who set those dimensions. So wherever you calculated an even number of steps, like 5 by 2, for example, maybe I use a different color here, those are good to name at the beginning of the game, because then you are guaranteed to win. So there is this dimension, or this idea in the activity too, that once you go and find all these steps, not only you can see interesting patterns in the columns and diagonals of it that you can all think about, but there's the game aspect of it too. And yes, that's a very good point in the chat. So if we change, Carol said that if we change to game 2, this will all change. And again, if you have a longer time to work with this activity, in game 2, these things do change. And it's wonderful to compare them. Are there games or are there dimensions where it doesn't matter whether you play game 1 or game 2? You get the same kind of result in terms of who wins.
Could you repeat the rules of game 2 for those that?
Yes, so in game 2, a person is allowed to draw in several squares, but they have to be the same size squares. So if let's say we have that example, which is a little bit like one that we did before, 17 by 52, right? So player 2 can draw in a 17 by 17, but actually can draw in another 17 by 17. And even another one, because 3 times 17 is 51. So as the first step here, player 2 will need to draw in all of the 17 by 17 squares that they can. So this will just be one step, drawing in all of them. And now it's player 1's turn. It's 17 height and only one length left. So the largest square you can draw in is a 1 by 1, but you can draw in 17 of them. So player 1 will draw in all 17 of those 1 by 1 squares. And that ends the game. So the 17 by 52 game will have just 2 steps. And player 1 will win that game. And the maybe interesting connection of this in terms of higher grades, if you teach middle school or high school, this connection to greatest common factors, in fact, what this game 2 and to some extent game 1 also gives you is the Euclidean algorithm of finding the greatest common factor. And game 2 gives you exactly how many divisions you do in this Euclidean algorithm to get the greatest common factor. And this table is really interesting for game 2. So if you find some more numbers here, this would look like, I think, 1, 2, 1, 1, 2, 3, 2, 1. So now you can see that, for example, that first column is not 1, 2, 3, 4, and so on. It's all ones, because a person can draw in all the 1 by 1s at the same time. This row becomes something like this: 2, 2, 1, 1, 3, 3. And you can, of course, do all of this without mentioning any of that algorithm, or do that. But again, a little bit more will reveal sort of interesting patterns in the columns. Which is always a fun thing. So if there's enough time and you fill this table, there are many things that could jump out at you about these columns. And then also numbers, right? So one interesting part of this is if you go up to here, all of the numbers, all of the steps, it's less than or equal to 2. The first 3 appears with a 3 by 5 rectangle. The first 4 appears where you need 4 steps for the game with a 5 by 8 rectangle. So those numbers are some famous numbers too, which is a really nice connection. So these become the Fibonacci numbers. So there's sort of a magic connection to Fibonacci numbers too. And I wanted to show you another kind of extension, just very real quick. There are these mazes called area mazes. Maybe some of you saw these. It's a Japanese puzzle maker, Naoki Inaba, who invented them. And the idea is to figure out either unknown areas or unknown dimensions of rectangles from the given information. And if you just Google area mazes, you can find many of these problems, which are slightly different, but a little bit connected to dividing sometimes rectangles into different other rectangular areas and figuring out their dimensions. Some of these are hard. Some of them are easier, right? So for example, here, the idea is that we have to find the area of that on a rectangle where the question mark is. What do we have to go by? Well, this 16 is the area of that rectangle, which turns out to be a square because it's 4 by 4 gives us 16. So you know that the other dimension of that rectangle is 4. So now you know about the 20. Once you know that that side must be 4 by 5, Now you can go to the 30, one dimension is 5, so the other must be 6, and now we know the area here. And there are these, you can make these really, really hard too. So you can find a great connection or collection on the internet with varying difficulties. And sometimes it's not always rectangles that are divided up. So these could be fun logic puzzles for kids also. And I think my time is mostly up, right?